Yes,
Yeah,
finished.
perfect. So we can
Yeah.
start now. Yeah.
Yes, sir.
Thank you. So welcome back. So I mean, this lecture we have to stop at 12 o'clock because there's a talk at 12:15. So we will stop at 12, but we will continue afterwards, right? Yesterday we started the yesterday we started the discussion on the Bluetooth data set, um, and we are going to continue that today. The way the Bluetooth technology works is generally you have a master device and you have a slave device, right? So there are different process in this whole one. The master device, okay, so the processes are, there is an inquiry process and there is a page process, and then finally there is a connection happening. So let's say these are, I'm just making, these are two Bluetooth devices. Let's say this is the master who wants to actually pair up with someone. This guy is going to send an inquiry. Just keep on sending inquiry signals out. The inquiry signal will be scanned by another device, which is here. So this device gets inquiry signal and they might respond back. That is the inquiry process. Then once it has responded back, and the master is then going to send the page. The other device is going to scan the page and send the response back. Finally, there is a connection happening. So it's a whole communication process as you see here. Now, sorry, it's phaging. Like they are basically like they want to activate the connection. So here, because the inquiry signal can be keep on sending. Like I want to, like for example, if you turn on your laptop and you scan for the nearby Bluetooths, you will know number of Bluetooth options that you have. But then you click on one of them to click connect with them, right? So you will know what are the nearby active Bluetooths around your area. Now this concept basically is the one which was used as one of our complementary source of traffic data set. You're not interested in connection at all. You do not want to connect with other device. You only want to basically figure out, okay, you just call out and say who is around me. People will say, okay, person A, person B, person C, that's all. You only want to know who the people are around you. And when in this whole communication process, you only want to read the name of that person, which is the MAC address of the person. That's why you're only interested in the discovery process, not in paging or connection process. So if I have a device which is always in the inquiry mode, keep on sending inquiry signals out and getting the inquiry response, that device is capturing the MAC IDs of the nearby Bluetooth devices. That's the only outer concept behind it. So in actually Brisbane or like in other places, let's say this is a place where you have the Bluetooth antenna. So you have put a Bluetooth scanner somewhere along the road, and this scanner is basically sending the signals out in the inquiry process, can keep on capturing the MAC ID. So you can have a master device placed somewhere along I can put a master device here, keep on inquiring the MAC address. I can figure out maybe how many MAC addresses are there by. But this other device has to respond back, right? Now, obviously, it depends on how far communication you want, and that depends on your hardware. You can have different type of antennas depending on how far you want to scan. Like you can scan for 5 meters, 10 meters, 15 meters, 20 meters, 100, 200, 300 meters, depending on the strength of the antenna. Like for example, I can have a scanner here with a scanning zone. So antenna based on its strength, basically this is antenna strength. As the strength increases, your communication range starts increasing. Yeah. Now, in the case of traffic and transport, you do not want to just have 5-meter scan zone. You want to have a bigger scan zone. So generally, you are at 100 or 150-meter scan zone that you're looking at. The reason behind this is it might take some time for this whole process to happen. Generally, around 5 seconds is what you need to have a 98% of the IDs to be captured. So it means that I need to have 5 seconds for a vehicle to be in my scan zone to scan it. And depending on the speed limit of the road, you figure out how big I need my scan zone. Antennas can be of different shapes. You can have an omnidirectional antenna capturing all the directions, or you can have a direction antenna only focusing on one direction. Just to tell you that basically it all depends how you configure your scan things. So the concept is very simple. I have a master device which has a scan zone, as you can see here, omnidirectional scan zone, 100 meters. Each time you have a Bluetooth equipped, so important, Bluetooth equipped electronic device, which should be in the discovery mode. Like all the smartphones these days, basically they actually sleep after a while. Like only you turn them on to be in the discovery mode, but they should be there. These Bluetooth equipped devices, when they are in the scan zone area, and they are able to communicate with the scanner is just trying to capture the MAC IDs. That's the only thing it's trying to capture it. Scanner has its own time clock. It knows the time it has first observed or time it has observed the MAC ID. So what you get is MAC ID and the time. These MAC IDs are unique identifiers of the device. So that basically is an important thing. One thing which I want to highlight here, like this thing came up when I was analyzing the data from Brisbane. I was never told when the data was given to us. We did the analysis. Even today, the scanners that we have in the city of Brisbane, they have an inquiry cycle. So the way it works is, it inquires for a certain amount of time period. Whatever MAC address it gets, it stores them with that time period. So let's say it's inquired from 0 to 14. Whatever MAC address gets in that 14 seconds, it stores them at the end of 14 seconds. And the timestamp is that 14-second end. It's not the time when it has observed. Then it scans again, scans again, scans again. So that's the inquiry. I just named it inquiry train. But more advanced Bluetooth scanners these days can just continuously keep on scanning and storing the MAC address with the time. But that's how the device was there 10 years back. Even today, it is the same thing. So now imagine this is a scan zone. X-axis is the time, y-axis is the space. I mean, the reason I spend so much time in time space because a lot of my discussions are using time space. Imagine this is a trajectory of one of the Bluetooth vehicles, and this is my scan zone, and the time TA is the time when the vehicle has just entered the scan zone. But you will not be observing it straight away. You might take some time for observation. Let's say time TFD is the first time when the vehicle was discovered, and that was an inquiry train. So the Bluetooth scanner might be storing this first observation at the end of the inquiry train, or whatever configuration it had, right? So it can be the first or it can be the last, but it can be storing at this point. Then this vehicle has left the scan zone there. From here to there, it might be observed multiple times. It's not just one time you might have observed. You might have read this name multiple times. And at time 3D, the vehicle has left the scan zone, but maybe the last communication was at 3LD. And the corresponding inquiry train is this. So TLR is the last reported record you had. Maybe it was observed maybe 10 times, 20 times within that time period. Now you don't want to store each and every time it was observed. So the way they store the data set, at least in Brisbane, the scanners that they have the MAC ID. They store the first time it was observed and for how long it was observed, the duration between first and the last observation. So that's what you store. By doing so, you are basically reducing the number of time you have to store the data set. But from here, you have to see a few things. You're not observing, you do not know where the device was in that scan zone. What you only know when it was first observed and when it was last observed. It can be anywhere within the scan zone. I've shown it quite beautifully that it is that much radius, but based on communication, strength and based on the weather, whatever it can impact, this radius might have some fluctuations also. But so there is a spatial error in observing the Bluetooth MAC ID. Spatial error because it's observing in a specific space. So I call this error EA or epsilon A for its arrival error, and maybe epsilon D for its departure error. So there is an error into the whole observation. Are you okay with this? Only the timestamp, right? Only it timestamp and the MAC ID. Yeah. So you know the MAC ID and you know the timestamp it was first observed, and then you combine all the observations and you give the duration for how long it was observed. Sorry? Oh, because it takes time for the device to come. It's not like you are having automatic number plate recognition system focusing on the number plate, and when you do that, you are focusing at one specific location, so you exactly know when that number plate was there. Or it's not like an RFID tag reader where you exactly know when it was there. You need time to communicate. For example, if you open your laptop, click and try to figure out your nearby Bluetooth device, you see that it's not instantaneously you can see that, right? So it takes some time. So that time gap. So the vehicle has entered a scan zone area, but it might take some time for it to identify that what was the MAC ID. That can be 5 seconds, or that can be 3 seconds, that can be 2 seconds. So generally, in the case of communication technology, it takes within 5 seconds, you will have 95% chances of observing it.
Why not we use TFD time FD value?
We don't know that. I mean, because see, I'm just telling you in the way they are storing it, right? So they are that actually you are scanning it for a while, and you just say, okay, I will scan that many, just store it, dump it at that time. Yes, you can use TFD also, and I think more advanced scanners nowadays are storing TFD. So I was just telling you that this was a technology that I studied 10 years back, and even today it is used that way. So the concept here to tell you that you have to understand the data source, that how the data is brought to you. So when this data was given to me, it was only given to me like this, and there was a meta file telling this is a MAC ID, first observation, and the duration. And we started playing with it. But I wanted to go deep into to have understanding. And this inquiry was never told to me. How do I come about this was from here. We tried to look at, this is a time series of the MAC ID observed in the city of Brisbane for the whole day. And you plot the time series. For the whole day, you don't see much, but if you zoom it in, I observed one device observed here, other device observed again. Sorry, that observation, the time gap between observations. So we have 6 observations at this time. After a certain time, we have, let's say, other number, but there is no observation from here to there. And we found a pattern that every 14 seconds or something, this observation is happening. So it was from this analysis. And we went back to the agency and asked them, look, we are observing every 14 seconds. Why it is like this? So one of the engineers told us that the device has a scan cycle. That thing was never told. In fact, when they give you data, you don't know that. And the technology was quite new. We didn't know much about it. And during that discussion, another thing came up. They said that their scanner has a scan capacity. Means in every scan cycle, the maximum it is scanning is 14 MAC addresses, or a 15, whatever the number was. I don't exactly remember the number, but there was some scan capacity. I think it's 5 MAC addresses per scan, whatever it is, right? So it means that you will not be storing more than that. That really helped us when I was doing an analysis for mains or Western Australia. They wanted us to study the penetration rate of the MAC addresses. How much is the penetration rate along the road? So when you study the penetration rate on the arterial network, it's a good penetration rate because your traffic is less and you're observing more. Let's say you are observing 15 MAC addresses and the traffic is, let's say, 100 vehicle, 15% for just for number sake. But when you take the same thing on the motorways, the penetration rate was just 3 to 4%. Why? Because scanner has reached its scan capacity. Motorway has a much higher traffic. 4 lanes, much higher traffic. So when you reach the capacity, no matter how much is the other traffic, you will not, so that penetration it starts decreasing. So that I was able to answer because I knew that there is a scan capacity. Then I told them that, look, there is a scan capacity of your scanners. That's why there is a big difference in the penetration rate between the 2 locations. Yeah. For example, here another observation. Yeah. Always try to see. I will try to see what's behind it, and that's what I was telling you in the case of big data. That do not just take it blindly. Always try to understand how the data is collected, because then you are able to answer, or at least you are able to better understand the results. Results will be whatever they are, but you have to explain them why they are the way they are. You will be able to better explain that way if you understand what's the process behind it. Like for example, this is a time from midnight to midnight, and y-axis is the observation gap. So gap between 2 observations. You can see that majority of them is having a 14 seconds. So that's how we came to know it is the 14 second is the scan cycle. Now, I mean, like this is still in Brisbane like that, but there are number of advanced Mac scanners these days who doesn't need to actually do the scan cycle. They are actually getting quite frequently. But when you are installing these scanners, you're installing them with the life cycle of maybe 10 years or 15 years. So it was installed that way, and still we are getting the data in the same form. Yeah. So when I understood all these things, we basically worked on simulation model. We said, look, we want to perform, because you do not know the accuracy of travel time and all those things. Let's try to study the accuracy. So we tried to build a communication traffic Bluetooth communication simulation, which is very simple. The vehicle has entered. There is a probability distribution of it to be observed in certain time interval, and there is a scan cycle of 14 or whatever scan cycle we put. So whatever I have explained here, we try to write a code that can, if I have a trajectory of the vehicle, there is an error distribution that you figure out, or the probability of its observation, corresponding cycle you have, try to simulate this data set. So we actually build that simulation in simple MATLAB. We have a traffic simulation. When it can be AIMSON, VSIM, whatever you want to do, you can simulate your traffic, and then you can communicate, like you get the vehicle trajectories, you give it to the communication simulation, try to replicate the Bluetooth data the way it should be, and then use that to study the travel time and other things. So I would like to just show you here that what we tried to understand was, obviously, if the scan cycle is going to increase, your travel time accuracy is going to decrease. That makes sense. Like, you are going to have a higher scan cycle, you have a more error. Similarly, if the scan cycle is going to increase, your reliability of the travel time is also going to decrease. And same is for the penetration rate. As you increase your penetration rate, your average travel time estimation is going to increase. That makes sense. If I have more penetration rate, I will have more sample size, and I will be able to have more accuracy in my travel time estimation. Now, this is the actual data set from the city of Brisbane. You have an ID of your data point. You have a device ID. So generally, you have to encrypt the MAC IDs. There is a lot of not debate. There is a lot of concern about the privacy, especially in the developed world. That if the MAC ID is there, it's a privacy. It's a unique ID. So you have to encrypt it. So they have encrypted the device ID. Then there is an area ID, means the location where the scanner is installed. So that's the unique ID of the area. So you have, let's say this is 10274, might be, let's say, intersection at the intersection of, let's say, Old Cleveland Road and the Newnham Road, one intersection. And you know the XY coordinates also from some other data set. The time it has entered, like it has 2020-0501, at that time of the date has entered, duration for how long it has entered, 45 seconds or whatever. Yeah. And that's how your whole data set is. And this is actually quite latest one. This is from 2020. And we have been collecting this data for last 10-11 years, because we have a direct access to the system to actually grab this data set.
What's the purpose of area ID?
Area ID is the location where the scanner is. So let me show you like this. Sorry, where it is. This is the city of Brisbane, right? This is the city of Brisbane, and these are the locations where I have the scanners, all these markers. So this scanner has an area number of 80262. Other scanner has the area number of 1057. So area ID tells you where the scanner is. It's just a geo-reference of place where the scanner has been installed. No, this is an area ID. Just there's no standard for it. You just give a name to it. A name for your database, that okay, this is the location where I have the scanner. You are going to give a name to it. So it is actually the name of, it is the ID of the signal controller that is installed at that location, because they have their own database of all the signal controllers. So that's the location where you have it. Yeah. So that is, let's say, a different device ID, area ID, like this device. If I just sort it out based on a specific device, so you have a huge database. You can say, let me just get the data for the device ID 4. You get this device ID, and you can figure out what area it has been observed, or what location it has been observed, at what time it has been observed. So technically, you know where the vehicle was. But before going into detail, I would like to, something else came to my mind now. This encryption actually is actually important for privacy, for the government. Although I personally do not think that it is that much. It's my personal opinion or my personal view that the MAC ID is that a big threat to the to to the privacy, because we don't know the MAC IDs. Do you know the MAC ID of your mobile phone? Do you know that? Maybe you know it, but not everybody knows that, the MAC ID, right? And there is no centralized database which is linking a MAC ID to the owner. So that means that it's very hard to trace that. Even if I figure out the MAC IDs in the nearby area, I do not know who it belongs to. Having said that, the automatic number plate recognition system, a question was asked in the previous session, that ANPR. You have the cameras on the road focusing on a specific stretch, specific location. Its job is just to read the number plate. They are designed to read the number plate, and you definitely install them near the toll booths because of the reason that you don't want people to just don't pay the toll. So they are definitely at the toll booths. They're at the congestion pricing location, like in London. They're almost everywhere, so that they are capturing the MAC ID, the number plate. Number plate has a direct relationship with the ownership. There is a database which can link your number plate with where who is the owner of the car. But there is no such direct relationship between a MAC ID and the owner. So I personally do not think that there is a big privacy concern there, but government wants to, or the agencies want to be more, I would say, protective, and they said, oh look, we are going to encrypt it. The challenge I am facing in Brisbane, even today, is we have two major agencies, Department of Transport and Mains Road, which I told you earlier, managing our motorway section and the nearby arterials. Brisbane City Council, which is managing the intersections, the arterial network. Two separate agencies having a two separate encryption. So if I look at the whole Queensland region, I cannot merge them together. That is a challenge which is there, because they are done by two separate agencies. So this encryption, and in fact both of them are installing scanners almost at the same time. So that is the challenge. And I told you earlier, like, your road network is managed by different agencies. They want to make the road safer, they want to make the road better, but quite often we do not have that institute level coordination done because of whatever reasons they are. So I do face, this is what I'm showing to you. I believe it is from the Brisbane City Council network, but if I show you from the TMR network, it will have a different, so I cannot match it. But the good thing is their inscription is fixed. If they have fixed inscription, then that is fixed for the last 10 years. It's not going to change. So I can at least trace, or I can study the mobility of the people or mobility of the device over last 10 years for the same jurisdiction. So now this is what I want to show you. Like, this is a MAC ID number, whatever it is, number 4, or maybe this is not the, what's the MAC ID number here? Whatever it is, let's say this is the MAC ID number. Sorry, 1 second. Don't worry about the data set. Let's say this device was observed here first, then observed here, and then observed here. And we know the time when this device was observed, right? So actually these are details of that location, the XY coordinates, the area ID, and all those, and all these details are the details of that location. This is not the details of the MAC ID actually. So
it takes some seconds to capture.
Yeah, there was, in fact, when long time ago I went to the department, said we can do some study to do some research where you should be installing the scanners. They said we don't care about it. Why? Because the scanners were so cheap. They were just $500 for them. And they said we already, all the locations where they have the traffic signal control system, they have all the communication technology already out there. Only thing they have to do is just put the scanner there. That's all. So they don't want to worry about where they want to put. They're going to put everywhere. So all the intersections in the city of Brisbane has scanners. It doesn't matter where they are. That has issues which I will talk later on. Issues, not issues basically. It's just, it is too much dense data set, but there are ways to analyze it. So it is everywhere in the city of Brisbane. But I will come to that question, and I'm going to show you a graph about the travel time, and then you will figure out what distance you should be analyzing. So I can have a scanner data here, there, but what distance you should have confidence in. I will come to that question. Now, if let's say you have two locations, two intersections, I have a scan zone. Let's say my scanners are here. There are two ways to get the travel time because the MAC ID is fixed. So I know this MAC ID was observed at location A at time T1, location B at time T2. The time gap is the travel time from A to B, right? From A to B is the travel time, but we do not know what route this guy has taken. We only know the travel time from A to B. So if you look at the time entered to time entered, you will get one travel time. If you look at the time exit, which is entered plus duration is the exit. So if you have entered at, let's say 7 o'clock, duration was maybe 10 seconds, you have exited at 7 o'clock and 10 seconds, right? You will have another travel time. So they are on the intersection. If you have to study the delay of the intersection, let's say delay of the downstream intersection, which of these two travel time you will be looking at? Both of them, one of them, none of them. If one of them, which one of them? Let's say you are interested to study how much is the delay observed at the downstream intersection. So is it entrance to entrance, exit to exit, or doesn't matter? You can use any of them and you can simply get that delay. Sorry? Both can give you some delay value. Yes, both can give you some delay value, but which one should give you a better delay for the downstream? Sorry? Exit to exit. Why? Okay, so exit all. So you're looking from here, yes, and then yeah, yeah. Okay, so if you look at exit to exit travel time, it tells you how long it takes to travel from here to there, right? Let's say it takes you 3 minutes to travel, just for the sake of discussion, 3 minutes to travel. If there was no traffic signal, no delay, nothing, and traffic might take maybe 1 minute to travel. So, but you observe 3 minutes, then that additional 2 minutes is the delay at the on this road, right? Does it make sense?
So why not we consider the beginning of the first and second circle?
First and second circle. Oh, sorry.
Entry time, exit time and entry time duration, and that second circle. Entry time, that difference will tell us the.
So I didn't get it. You're saying this one,
is difference minus this difference.
but this difference is okay. If you look at, if I say the time it has entered here and time it has left here, it's going to tell me the travel time from here to there, right? So it might take, let's say, 15 seconds to go from here to there, for example. If I look at this and that, which is actually the duration, let's say it takes 20 seconds to go from here to there. We have no idea what's happening in between. We only know what's happening in between these two locations. So a single Bluetooth data set is not telling you much. It's just telling you how long the device was in that area. That's all. But if you look at exit to, if you let's start with the entrance to entrance. Let's say the guy entered here at 7 o'clock. The vehicle was observed there maybe after 3 minutes. So what it tells you, it takes 3 minutes to go from here to there. Yeah. Now in that 3 minutes, obviously if you look at the traffic intersection, the queue will be formed here. The queue will be formed there, right? So a part of the queue you have captured, and if there is any leftover queue or spillover queue, you have captured that one. It doesn't tell you at all how much was the delay for this link or how much was the delay for that link. So entry to entry is not telling you any delay. Both of them are basically partial delay from upstream and maybe partial delay from downstream. But if you look at exit to exit, if it takes 3 minutes to go from here to there, then that 3 minutes includes your travel plus when you join the queue plus when you leave the queue and you exit that section. So it has that all the travel features. So it is exit to exit you can use to estimate the delay at downstream intersection. Does it make sense?
So if there is no delay, it's on the travel.
So basically what you will get is a travel time, and the delay will be the travel time minus the free flow travel time. So if they're under normal conditions, how long it takes? So if it takes only 1 minute, if there was no delay, there's no queue, it has taken you 3 minutes, means that 2 minutes was the additional delay. Yeah.
So I just have a small.
Yes.
Yeah. So here we are considering a very ideal condition where the stands are placed between junctions which are next to each other.
Yeah.
But if we place it some far distance, so how are we going to consider the travel time? Because the vehicles might take another route and then reach the junction where scanner is.
Yes. Very good question. We'll just come to this in the next slide. Okay. Just give me
sure.
2 minutes for this one. Now,
Yeah, sure.
this is, let's say you are able to get travel time between two locations, right? If I now start plotting those travel time values. So what you see in this one is the raw travel time matching, exit to exit between two locations. X-axis is the time, midnight to midnight. So entire 24 hours. Y-axis is the travel time. Each of the column here is a specific day of the week. The first one is Monday, second is Tuesday, Wednesday, and so on. It's the whole month of August in 2012, if I'm not wrong. Now, this is actually the travel time that you're observing from the network. You can see there's a huge scatter in the system. What can be the reason for the scatter? One reason that audience, I forgot the name, whomsoever asked that question, has already mentioned that you do not know which route that the vehicle has taken between two locations. You only know the time when it was observed at upstream, time it was observed at downstream. And between upstream and downstream, maybe the vehicle has stopped in between for whatever XYZ reason, or might have taken some route and then again observed at downstream. So you do not know that thing. That's why you can see the scatter in the system. Maybe a travel time of 2000 seconds was because the guy entered it upstream, but there was a let's say a detour he has taken and then came back, or some other reasons. So you do not know that, and you will no way you can know that. Other thing is, in the case of Bluetooth data set, you are not focusing on the cars or anything. You are focusing on the MAC IDs of the devices which is being transported by the users. So it is not that it is a car A or car B, it is the MAC ID A and MAC ID B. So that MAC ID can be taken by anyone. It can be me walking on the road, it can be a cyclist, it can be any XYZ person. It's just a MAC ID movement. It is not, that's why I call it, this is a complementary data source. It is not it's not a source of the actual car. Yeah. So I hope that answers your question that okay, yes, you cannot know which route that person has taken it, or this travel time is ideal if you are looking at two sections which are where you do not have those possibilities of moving around. What can be the other reasons for this spread? Yes, please. There's a question from online. Oh, yes.
Yes. Sir, I want to ask you one question regarding what if one vehicle has two MAC IDs and the Bluetooth scanner will be then considering those two MAC IDs being in the same vehicle as two different vehicles.
Yes.
So, how to tackle that and how to filter that?
That's another good question, and I will come back to this again the next slide after this one, which is, I mean, the question you have asked, there was a different question asked by the agency that if I have a bus with 60 passengers on it, I might be getting a lot of data from it. So how will you address that? Yes, I mean, as I said, the Bluetooth device is not differentiating between, we do not know what's the source, whether it is from a car or it's a bus, we do not know that. Yes, if I have two devices, I'm going to get that number of ones. But you cannot, because there's no way you know who is actually carrying it. Now, I will highlight one more thing here is, nowadays the Bluetooths are quite smart, right? They are like your mobile phone Bluetooths, they don't go into the discovery mode until you put them to be on the discovery mode. The Bluetooth that you are getting from the car, the inbuilt Bluetooth of the car, they are the dummy Bluetooths. They are always in the discovery mode. So most of the observations that you are getting from here, and this is just I'm just assuming, right? We do not know the device source, is from the dummy Bluetooth of the car. We did some observations. We did some experiments here in India in the city of Surat with Professor Srinivas Arkarkar. He tried to use a scanner which has both Bluetooth and Wi-Fi scanners. In India, we are getting far more Wi-Fi observations than what we are getting from the Bluetooth observations, because our mobile phones have always Wi-Fi on, but the Bluetooth is not on that much, and the cars that you are having here, like the Bluetooth might not have, in fact, like not all the cars have the Bluetooth features inside it. So you are having a high Wi-Fi observation than the Bluetooth. So yes, it can happen that you will, if you have 2 devices, 3 devices, you are capturing them twice or thrice, but it is very hard. It's almost impossible to figure out from where it is. So what can I do here? It's such a noisy data set, but this is a very valuable data set 10 years back, because before this, road agencies have to invest a lot in the traffic surveys. To study the travel time on a specific road, they have to hire people every 6 months to actually drive on the road to get the travel time values, to understand how the traffic is performing. Now they have a seamless traffic information from some source. I'm talking about 10 years back. There are other sources now also, but this one was a big, I would say, it has a big value for money. Just investing $500 on each scanner, 500 for scanner only, but there's a lot of other costs attached to it. You are able to save a lot of cost for your surveys. So what can I do to actually remove the noise? We'll come back to this one. August 17, yes, because you can see other ones. At least if you look at just from the density perspective, you have a high dense data points, right? 17, there was nothing dense. 17th August in, I think this is from 2012 or 2011, we used to have a Queen's birthday celebration. There was a public holiday in the city, and you can see that one from this data patterns also. So if you apply some filters, you can think of coming up with some statistical filters, apply the filters, and you can remove the noise. So we have applied one filter on it, but that is a statistical filter. There's not a filter that is taking care of the MAC ID number or anything. It's just a statistical filter. And if you apply that filter, you can remove the noise, which is focusing on get rid of all the data points which are not that dense. Focus only on the density of the points, right? So one way to apply the filter is, the one that is implemented in the city of Brisbane is median absolute deviation filter, or the MAD filter, which is, what you do is you look at a specific time window, as you see here. In that specific time window, you define in any filter, what you do is just define an upper bound and a lower bound. Anything outside that is your noise, remove them, right? It's just about how you define your upper bound and the lower bound differentiates one filter from another filter. So you look at the median of your data set in that time window, median. You say my upper bound is median plus sigma times a factor. Lower bound is median minus sigma times a factor, and that sigma is actually a function of the median of the absolute deviation from the median. So all the data points that you have, let's say within these data points, you find the median of the data. You see each data is how much it is deviating from that median, and you take a median of that. Again, these are statistical filters. It worked well. The department was happy with it, and they started using it. But you need to have a filter to just remove the noise. The factor F can change. You can have a factor of 1, factor of 2, factor of 3. As you increase the factor, your actually upper bound and lower bound range is going to, or the difference between them is going to increase. You will have more data points, but you will also have more noise. You reduce the factor, you are getting less data points, but you might be slightly more confident. So it's a trade-off you have to make. They decided to go with F is equal to 2, and we're going with that. Not too conservative, and just work with that one. So that is the filter which I had applied here. and you are able to see at least the good peak and all those things. So if you look at this one is actually from, I think, a bit far away from the CBD road. It's an inbound traffic. When I say inbound, means it is coming in the city, and outbound is when it's going out of the city. That's how we call it. We use a term in actually Australia. That's why you see there's only one peak. It's a morning peak traffic only. Evening peak, if I would have done the other way around, change my upstream and downstream, I would have another one. So in the evening, you hardly see any congestion, but the morning congestion is actually significantly high. So free flow travel time maybe is if it is 250 seconds, the congested was 1,000 seconds, 4 times the free flow at the time. Yeah, but this whole day picture or whole month picture clearly tells you the patterns. What patterns can you observe here? One you have already identified. There was a public holiday. There was no congestion. What can be the other pattern? Saturday Sundays are very relaxed here. What else?
Friday,
So Friday, the column of Friday is not, yeah. You don't have a longer duration because this spread of this this time period tells you how long the peak was. So Friday you have a shorter peak and not that high one, right? That's a good observation. What else? Monday, Tuesday, Wednesday, Thursday, Friday. So Wednesdays, I mean Tuesdays looks for me as the most congested one compared to other days. But again, so basically what I want to highlight here is you can, when you have a data like this, you can try to figure out different patterns. If I do it for the whole year, you might be able to figure out school holidays and the non-school holidays have a different pattern, or the travel time profiles are actually quite different. If I do it, if I had a link near to a shopping center, on Thursdays the shopping center is open until 9 p.m. in Brisbane. You will have an evening profile also happening. Even the Saturday will have a congestion because Saturday people go for shopping more than compared to Sundays. So you will have a different pattern happening on your data set. So if you look at the whole snapshot and you try to link the time of the day, day of the week, time of the day, and other features attached to it, you can easily identify those patterns in the system.
this is the time taken for that exit.
Exit to exit, yeah.
It also shows that the disorder, let's say, city. So the entry point and the exit point will be different.
Sorry, if it was?
The incoming point is not the same as the outgoing.
In,
So I will enter into the institute through that gate.
yeah,
But probably I will exit for another.
yeah.
Otherwise, at some other time, let's say people come to office at 8 a.m.
Mm-hmm.
Then they leave at 16 hours.
Mm-hmm.
Again, I should actually receive a contract.
Yeah, but this is from one of the roads. It's a road. It is. I don't remember which road it is. It was, let's say, it's a road like this, that much. A road may be a location here, location there, and you're only focusing on the travel time for this specific road. Yeah. But that road might have a cyclist, might have like the pedestrians also, and other sources of noise. That's why you're observing that kind of data set. Yeah. Yes. Okay, I think there's a confusion on entry and exit point. A scanner has a scan zone, right? What I was trying to tell here was each scanner has its own scan area, right? Scan zone. And when you put a scanner at a location, the location is fixed. They are permanently installed in scanners. They're not the mobile scanners. Location is fixed. Antenna strength is fixed. So your scan zone is fixed. And when you are getting the data set, you get the time enter, time exit. So I think your question is the vehicle can enter from here, vehicle can enter from there also, right? Any of this. Now what you're doing here is, which is like this. Let's say these are the MAC IDs, ID number 4 have been observed at 262, 157 and 130. So at 262 it has entered at this time, and that was the duration. At 157 entered at this time, that was the duration. So from here to there it takes almost like the 2317 to 2431. So these two locations, the time it has entered in this location, time it has left from that location. Now if let's say I have one location here, other location there. If the vehicle is moving in this direction, then the time entered here will be first, and the time entered here they will be afterwards. If the vehicle is moving in that direction, then the vehicle will be observed here first and there later on, right? So your order will automatically define in which order you have been observed. Yeah. Oh, that is based on the time entered and the duration. So entered plus duration is the exit. So if I go here, let's say this is the actual duration of the vehicle. Time vehicle has entered and the time vehicle has exited. This is the duration, the actual duration. But what you are actually getting is the time it was first observed, time it was last observed, and this is the duration you are getting, right? Oh, we cannot do anything on that. We do not know that error. I want to just highlight that there is an error. It is not a perfect system. You can't do anything. There's no way you can know the error. The good thing here is when you're looking at the individual vehicle travel time from upstream to downstream, right? You are making some error on this guy in terms of the time entered, time left. When this, and you are going to make some error in some other vehicle and so on. When you start taking an average travel time, these errors basically compensate each other, and you are having more confidence in the average travel time estimation compared to the individual vehicle travel time estimation. I don't have that directly graph with me, but if you go on, or maybe I'll show it later on if I manage to do it. If you go on the paper which I mentioned here, it should have that graph. That's the paper. It did talk about the average travel time and all those things. So when you took an average, it compensates each other, and you have more confidence in the average travel time estimation than the individual vehicle travel time estimation. Yeah.
So when the speed is increasing, then error is also, we are taking this is also high, because the pedestrian, what we call pedestrian, speed is low.
Yeah.
The inquiry time, it gets sufficient inquiry, so that SRE is getting it.
Yeah. I mean, speed and the error, I'm not sure how much relationship will be there in the speed and error, because it depends on how long it takes for it, right? If the speed and the observation will have a relationship. So if you are running at a very high speed on that corridor and your scan zone is small, you might not be even detecting that. So another important point here is you are not detecting all the vehicles, all the MAC addresses. You're only detecting some of them. So it's not 100% detection. That's another point with which you should know that. So generally what you do is, as I said, you need to have, you want to have at least 5 seconds for the device to be in the scan zone. And if I'm going to put this on a motorway which has a speed limit of 100 kilometers per hour, I'm going to make a scan zone of 250 meters. On the arterials where I have a speed limit of 60, I'm happy with 100 meters. So you are going to increase your actually scan zone based on the speed limit of the road, because you want to observe them. But yes, if the speed is high, if you only observe first, the duration will be 0 for that guy. Only one observation. Then you have higher error from that angle. Yes.
So based on this, have you done any vehicle transformation? Like if visitor speed may be,
It's become very hard. You can't do that. You cannot know the vehicle composition from here. It is, as I said, this is not focusing on the vehicles. It's only focusing on the MAC IDs. That's all. We try to do some study to see, because we also got the actual MAC IDs from the department, just based on our personal relation with them. They gave us the actual MAC ID also. We wanted to study where the MAC ID is a 16-digit, I think, number. The first 4 or 6 digits tells you the manufacturer. We say, can we see some pattern inside it? It's very hard because it is the chip that they talk about, and that chip can be in any device. It's very hard to actually figure that out. There is a IEEE database that relates the initial digits of the MAC ID with the manufacturer's chip, but it's very hard to figure out.
Any pilot study that you people have tried in moving from first Wi-Fi to the second Wi-Fi?
No, we have done those studies, but it is the MAC ID. It is a MAC ID movement. It is not the movement of the vehicle type. So I can be a bus driver, or I can be a cyclist. I can be a pedestrian. It is just a MAC ID. So it is, we do not know the vehicle type. We do not know what is the mode of transport. We only know that a MAC ID is being transported. That's the only thing we know.
Like you said that these bridges are actually intercepted, there were already some cameras and sensors available. So can like the data be included with a camera with a video?
Fusion. You're saying, can we fuse them?
Yeah, the
Yeah.
data can be fused and then more comprehensive output.
Yeah, very good question. I have that in the second half. When I talk about the loops, and I talk about how do you fuse them together, because single data source won't tell you the complete picture. There is one information you have. Here you have information about travel time only. We try to study, can we get the density? We cannot get the density from here, right? Can we get the queue length? We cannot get the queue length also. In fact, there was a work done by one of my PhD students where he started to figure out the duration correlationship with the queue length of the link. You can get a good correlation for a certain value, but the moment the queue length exceeds that scan zone, which will easily exceed on the arterial, the correlation is totally random after that. So for certain queue lengths, you will have a good correlation. After that, it just spreads out. So think about the delay observed in this region will be directly related to the duration value. But if the queue is further high, queue can be here, queue can be there, and so on. Your queue length just keeps on increasing or decreasing. You have no correlation after that. So it is very hard to even get a correlation between the queue length and the duration. Yeah. Yes.
Even when we are getting the peak, it might be that by different composition is high on that.
Mm-hmm.
We are getting the more travel time.
Yes.
We cannot differentiate like vehicle. There was no traffic, no problem with that, but travel time is high.
Yeah.
That is possible.
Definitely. I mean, basically, you cannot differentiate that. It depends. You have to know what is the road characteristic you're talking about. If I look at the Bluetooth travel time in the Brisbane CBD area where I have a lot of pedestrian activity happening, it's very hard. But if I'm looking at the area where I know there's a high amount of the car composition, there I will have more confidence. So the confidence of this data set depends on the characteristics where you are focusing on. Different sections will have a different confidence. There is no one single confidence for the data for the entire network, which I will present in the coming slides also. Yeah.
It's the noise. If we know the specific to location,
Yeah.
it's the for pedestrian we know the average speed. For other vehicles we know the it will be more than that.
Yeah.
So we can ignore that some outliers
Mm-hmm.
in the data part.
Yeah.
Using that,
So generally, when you do this kind of matching, the travel time between these two locations, you already have some heuristics attached to it. That the time gap between these two should be minimum and maximum. So if I show you this plot, the one I've shown you here, we put a maximum of 2001. Because this is just a MAC ID observation. I can observe a MAC ID A now, and this guy might have gone to the work and coming after the whole day, and I can observe him in the evening again. So if you do your matching like that, you can have an observation of maybe 18 hours. So, but you do not want, you say I'm going to cut it off after let's say a certain value, because I don't expect that this will have that actually bad travel time. So one way to do is that you assume a speed of let's say 5 kilometers per hour for the corridor, make a cut. So those are the heuristics you have to add in your algorithm. So I did not discuss the algorithm. I only said time A, time B is the travel time, but you have to add those heuristics. So here in this particular case, we put 2000 as the uppercut. Yeah, very good questions. So we use the median absolute deviation, but you can also apply any other filter like box and viscous plot filter. They will give you pretty much the same results, right? It's just the median absolute deviation sounds more fancy, and it has been used. And it has been used. It has been like it is currently used, and then we have to follow that procedure. That's what I was telling you. The city of Brisbane. This is the city of Brisbane. These are the traffic controllers that you install along the every intersection, right? And the shark fin shape that you see at the top is actually the antenna of the Bluetooth Max scanner. One interesting thing I will also highlight, Brisbane city, like each city has its own unique features. Brisbane city, all the traffic controllers, they have basically asked the local students or artists to just paint on them. So every traffic signal controller has its own Aboriginal painting or some student painting or something. They have a competition happening, and the controllers are painted like that. So anyway, so this is the Brisbane City Council region. It is more than 2,000 intersections. It should be a higher number now, but we have everywhere. The Department of Transport and Mains Road, which is managing the motorways, is putting on the motorways at again certain specific distance. There it is more complex because of the communication needs there, and it is logistically fixed with respect to wherever you have the electric wire coming and the corresponding, data ports and all those things. But you can see on the whole Southeast Queensland, various locations they had it. It's a quite old one. It's not a latest one, but it's just to show the spread. And as I told you, there are two separate agencies managing the network. Unfortunately, still today the MAC addresses are separately encrypted. How big this data is? I asked this question to one of my students. I asked him to just grab one month of data from the database. Tell me how many observations we are observing. So this is around 450 scanners within the Greater Brisbane region. It's not the whole network, but only Greater Brisbane region. We are getting around 3.5 million records a day, which is roughly around 2 to 3 GB data set a day is what you're getting. From the BCC network, you are getting around, from the 950 scanners that he analyzed, around 4.5 million. So effectively you get 8 million records a day or 10 million records a day for the city of Brisbane. Around 8 GB a day is what you're getting. The very good thing is this data is very well structured, as I've told you earlier. Device ID, area ID, entered duration. The moment you have a sorry?
So 5 GB per month?
Per month. Velocity and yeah, the volume is per month and the records are per day. I mean, these are simple CSV files, right? Although you're saying like 3.5 million records, just when you download it, store it costs you around 8 GB per month. It's not a huge in terms of GB. But when I'm going to talk about the public transport data, you will see the big difference. So it is well structured, so can be very, very easily analyzed. So there is not big rocket science behind it to analyze the data set. We used to get the data in the past using, like, TMR used to give us, BCG used to give us, we put it into MySQL server. Okay. So one thing I want to highlight here is the need for active visualization. Yes, you can do the analysis, generate the plots, but when you have a data for the large network, or even without large network, there is a need for visualization. So I will highly encourage you guys to start looking at the ways to visualize the data set. And that led to a totally different, I would say, research in my team, the better way to actually visualize it. We started looking at the data set for the entire city. So now one of the questions you asked about how to manage the congestion, how to study the impact of congestion for a whole network, is to look at the whole network like this. So we tried to build some dashboards. We started building on some dashboards on this. And in fact, I must say that this whole work started with one of the interns from S&IT coming to us. We asked him to just, can you start building the dashboard for us? This is one of the dashboard which I'm showing to you. You click on the link. So all the processing is done at the back end. You click on the link for the whole day, you get your speed profile. So you know the travel time, you know the length, you can get the speed, right? Speed profile. Plus you can know the traffic characteristics or the travel time characteristics. So the bottom one is the travel time statistics. You can extract various statistics from there. This way you can have a better understanding of different links, what you're getting. Yeah. Then if you click on a link, I want to see how much sample size am I observing after basically applying my filters on it. So x-axis here is midnight to midnight, and you select a month. Let's say there's a month of July. Y-axis is the different days of July. Different color represents the sample size for that time interval. I think it was every 1 minute. So every 1 minute, what was the sample size after filtering, right? So red means 0 or 1 to 2, 2 to 3. I mean, basically the 0 is red until 2 to 3. After 4 to 5, it starts becoming green and so on. And when there's no data, is null. What can you see from here? What can you infer from this? Is for one of the links here. So one of the road, which is Brisbane City Council Road, length is 1.88 kilometers, speed limit was 60. So you also add the spatial features on it, so you know which road you're talking about. So that's for this specific one, for this month, this is what I get. What observations you can get from here? Good, yeah. Brisbane is a morning city, yes, 5 a.m., yes. So this is as per your expectation? Yes, because you don't expect too much traffic or too much observation in the midnight, during daytime, and is green. Very good. Number of total samples for the whole day, around 3,000, and it is varying from one day to another day, which makes sense, as we have seen that weekends might have a lower travel time compared to weekdays, and so you not have a consistent one. It makes sense, right? Let's go to another road. This is Coronation Drive. It is 3 lanes. If I go to the next road, Milton Road, it is only single lane in one direction. Look at the sample size, it is more red. It makes sense. I will have a less sample when my lanes are less. So it is 1.6 kilometer section, but you have less sample. If I go on some other road, which is Old Cleveland Road, around 1.24 kilometers, I have a lot more red here, which is not good, because more red means I have less sample. It's an arterial road. I need to have some sample to have more confidence. So my travel time for that road will have a less confidence compared to the other road. Gympie Road, 1.92 kilometers, very green, perfect. It's a state controlled road, 70 kilometers per hour. I mean, basically when your high speed roads are basically managed by the state one. Around 2 kilometer section, lot of green, but one of the days, because of whatever reason, we didn't have a data set, right? So, but it is very good sample you are observing there. The other part of the road, the data was working, you're getting good sample. So what I want to show here is your spatial temporal coverage is not the same over the entire network. So the question was asked, like, how much confidence you have. It all depends on the site characteristics. It all depends where you're observing the data. You cannot say that my blue data is perfect. You have to study where you have installed it, what is happening in that region. Yeah. This one. Sample size is low here. It's a single lane. So red means sample size is between, let's say, 1 or 2 or 2 or 3 every minute. So every 1 minute you are observing only 2 or 3 sample only. By the way, I'm saying it low, but from the perspective of traffic engineering, it's a very good sample. You will never have, there's no way you will get that detailed information for that time period. But it is low sample, it means that I will have less confidence. So generally what you do with the Bluetooth is, you want to know the average travel time from A to B, right? So if you have 5 vehicles, average of those 5 is your travel time. If you have 10 vehicles, average of those is the travel time. Now, more is the sample, more is the confidence you have. Less is the sample, less is the confidence you have. If my sample is low, I will not have much confidence. For example, if I go in the initial plots, I show it to you. This one, you can see here, this one, I'm not able to make any filter out because I don't have enough data set. The filter, even a filter that point is there. Now, why that one is there? It was a question asked to us, and one of the engineers told us maybe because this is a Monday morning garbage truck who is always going in that region, and that might be the sorry, that road clearing truck, that might be the one whose MAC ID you're observing, and that's the travel time you're observing for that one. We don't know that. We did not go and cross check, but the site engineer knows about that site quite well, and we observe this pattern for on this Monday. He said it might be that one, but we don't observe him on the other days, because on other days we have other data sets to filter it out. On this specific day, there was not any data set to actually filter that one out. Yeah. So yes, it actually, I mean, if you have a less sample, I cannot, my filtering will not be strong. But these are the filtered ones. These are not the non-filtered ones. But my confidence in my travel time estimation will be lower, or average travel time estimation will be lower. Yeah. Okay. Then obviously this is the work done. Then one of my PhD students was quite keen. She applied. She said, okay, you have the data set for the whole network. We have generated the plots. Can she apply some machine learning to do the forecasting? Yes, she applied CNN based algorithm to do the forecasting. Very good. Published paper. Happy. Got a thesis. I don't want to discuss about the machine learning algorithm here. What I want to highlight here is, if you are applying machine learning, which is a very strong tool, very important tool these days, very well I would say established in the sense that you don't even have to be a computer scientist to apply it. The packages are there, you can apply them. But please do not apply them blindly. That's the important thing I want to highlight to all the students. Go to the fundamentals, understand the fundamentals, please. Because the results will be whatever they are. Whenever I discuss with my PhD students, I discuss the results, but I'm not concerned about the results, whether they are good or bad. What I want to know is why the results are the way they are. You have to explain me that process. Even if it is bad, explain me why it was bad. It's good, help me to understand why it is good. But at the end of the day, we want to publish papers like my model is giving 5% accuracy than compared to the model in the literature. That's fine. You can always find ways to show that, and there's a number of papers that way. But understand the foundation, explain the process. Critical thinking matters a lot. A blind application, in fact, I have few computer science graduates in my team. You give them the data, they will give you some outcome within 1 or 2 days. Something will always coming out. Why? Because they are very good in programming. They will get something out. But that's not what we are aiming for. We have to figure out what is the process, what you have done, why you have done the way you've done, and you have understanding of what's behind it. Unless you have an understanding of what's behind it, you will not be able to interpret what's ahead. Yeah. There will be always a biasness in your data set, aware of that biasness. Like as you can see, some sections have more sample compared to the other sections. Some sections have low confidence compared to the other confidence. So if your study area is the area where you don't have enough confidence, you will have naturally higher errors compared to the other ones. If you're only training your model on the one which is having the less errors, then there is a biasness in the system. Transparency and explainability is always important. In fact, it has been always highlighted in the machine learning world. The explainable AI is actually there for this reason, that you should be able to explain what's behind it. One thing which I not added here is, which I mentioned earlier also, is reproducibility. Your work should be reproduced by the next generation of the researchers, whomsoever. Like later on in day 4, I will just show you my research program, the way I am doing my research. It is not just one-off thing, it is things carried away from one generation to another generation. Like even this lady Sarah, when she applied this algorithm, the work done by the previous researchers on travel time estimation, I was very confident that this has been done. She can simply borrow that code, get the travel time statistics, get me the plots. So there is basically a continuation happening, and she can be confident on that part. But when she is applying that, when she finds any error, we have to report that error. And And one of the ways to do it is basically the version control of your codes. GitHub is a very good tool to do that. So that's what I want to say. I don't want to talk about this machine learning one. If somebody has to talk, I think Sarah is the best person to talk about it. Any question on this? Do you agree with me on that one? Please, because most of you are either you're a PhD student or you will be a PhD student down the line. Please keep this thing in the mind. Results will be whatever they are. It is that you have to explain the results. That is really important thing. If you're able to explain the results well, even if they're not good, you have the contribution in the state of the art. Don't just focus on getting the best results out. Now that's the plot I was talking about. You asked me a question like how far or how close the link should be. Here, x-axis is the distance between the Bluetooth Mac scanners. It is from simulation, by the way, the one I mentioned earlier. Y-axis is the percentage error in travel time estimation. And you have different plots. In fact, I'm thankful to the reviewer when I submitted the paper. The reviewer asked a question. So whenever you are submitting a paper in a journal, you will have number of good reviews. That reviews help you to think more and enhance the quality of the paper. So one of the questions was asked, and in the response to that question, I generated this plot. So x-axis is the distance. So what can you infer from here? What can you infer? If the speed is high, so basically 10, 25, so higher the speed means error is high, right? Lower the speed, error is low. Why is it? Why the percentage error is low when the speed is lower? Observation time is? Processing time is sufficient. Sorry, can you? Okay, let's start one by one. You first, were saying?
Speed is less, then the scanners are getting more time to
Scan, okay,
and the speed is high, so it might not be sufficient.
okay. But this is the average travel time from A to B. Yes, you will have more observations. That's good. So it is going to increase your sample size when the speed is less compared to when the speed is high. That's actually a good point. So when the speed is less, your sample size should increase, and that's also contributes to your lower error. That's good. What will be the other reason?
So as we discussed like earlier, we may get the end time, we might not get the out
Time. Yes.
We might get the out time.
Yeah.
The end time.
Yes.
So if the speed is high,
Yeah.
the scanner would be able to only catch one or
Yeah.
one or the
Yeah.
So
That might be another. So, which is same as like basically higher the speed, lower the sample you might get, perhaps, right? Okay. What else can be the reason? So in this particular case, my sample size was actually high, right? So the samples I've tried to get rid of sample size issue here, but that is a very valid reason. What else can be the reason? When you say overlap, what do you mean by overlap? Yeah. There is overlap.
Because when the distance is more, the error gets reduced for all the
Errors get reduced for the speed. Okay. I mean, if there is an overlap between the scanners, I will not trust the travel time at all. The moment the overlap is there, you are not going to do the travel time study because they are so close to each other. One thing which we have shown, the errors, the error is a spatial error, right? So what is the maximum value of the error you can have? So if I look at this, where is the diagram? Oh, that's the error, right? The maximum error you can have is basically fixed, right? The spatial error we will have in this region, right, is more or less fixed. So errors will have a maximum value. It won't go beyond that. So your travel time, let's say you are making an error of 5 seconds or 10 seconds, right? Let's say 10 seconds is the error you are making in your observations. But if my link length is going to increase and my travel time for a shorter link might be was 60 seconds, and 10-second error means you are making more percentage error, whereas if your link length is let's say is longer, your travel time is 600 seconds, then you are making much lower percentage error. So it has to do with the how far they are and how close they are from again that angle, right? But the further you go, the less sample you will have, because the traffic will keep on moving. So you will have another issue with the sample size there. So it's a complex thing from again that angle, and it's good that you guys have identified actually the reasons, and that thing contributes to this graph which I have shown, that as your distance is going to increase, your error is going to decrease if your penetration rate is not impacted. But the penetration rate is impacted, your error is going to increase also. But between two locations, as the speed is going to actually decrease, your errors are going to decrease, which is good because during congested conditions, traffic will be congested, your travel time will be larger, so your percentage error will be lower, which is good for us, I mean, in terms of analysis. Because for free flow condition, we don't care much. We know that the traffic is free flow. It is only during that peak period I actually care more. Yeah. Yes. Oh, this is from simulation. I told you this is from simulation. Yeah. It's not the real one. Yeah. I think we have to stop here and I will continue the discussion for this turning proportion, where we have another session after this.
Excuse me, sir.
Yes, you have a question, please.
Yes, can you please repeat what's meant by penetration rate?
A penetration rate is the proportion of my traffic that I'm able to observe. So let's say if on a specific road I have 1000 vehicles which are moving, and I'm only able to get, let's say, 100 MAC IDs. It means that my penetration rate is 100 over 1000, which is 10%. So the percentage of the traffic I'm able to observe. And your penetration rate for the Bluetooth is going to vary around maybe 12% to, 10 to 12% at one location easily. It's not a huge penetration rate. So more is the penetration rate, more is the sample size, more is the confidence I have in my estimation. Yeah. It's good. Do you have to go to another place? At what time?
Yeah, I think we can.
We can move there? Okay. So we will start at what time you're starting? And meanwhile, you should think about this question: can Bluetooth provide turning proportion? This is another question asked to me by Mainstar Western Australia when I was analyzing the data set. So all these are the questions asked by practitioners. You have one intersection here, second, third, fourth, fifth. They said we have all these locations where we have a scanner. Can I just match the percent of the traffic going in this? Because you can know that a MAC ID observed here, here and there, observed here, here and here, observed along this corner. So if I can it help me to give me what is the turning proportion? So what proportion of my traffic turns left, what goes through, what goes right? Can I use my Bluetooth to get that one? We'll discuss that later on. So think about the answer for this, whether you think you can or you cannot, based on whatever we have presented.
Okay.
Yes.
So I think Professor Bhaskar will continue this discussion. We'll have a departmental meet now. So you can go for lunch, and we'll start the next session from 2 onwards. Okay?
Yeah.
And for the students, especially from here, or others also, you can free to join. You can join in the Department of Civil Engineering. Professor Bhaskar will deliver a talk. You can interact with other topics also. If something of your interest also if you wanted to discuss, that discussion can be done.
Yeah.
Okay?
But if you go for lunch,
yeah, you are free to go
for lunch,
Yeah.
and you will bring me here by 2 o'clock, right?
Yeah.
So
2
we start
o'clock
at 2.
we'll start.
So maybe bring it 10 minutes before
Yeah.
2, because we have
Yeah.
plenty of things to cover.
Yeah.
Yeah.
So please be on time so that we can start the next session on time. So.
Yeah.
How long is the department?
This one will be for
1 hour.
1 hour.
12 to 1.
Yeah.
But I think I'm going to give a talk there, which will be more or less, I'm also cover things here, right? So if you want to go for lunch and take some break, you can go, because I think it will be long for you guys. Yeah. And online audience, we are going to meet at 2 o'clock, right?
At 2 o'clock, yeah.